Thank you very much. Hello, everyone. It is my pleasure to give the floor to Vincent T'kindt. Vincent is a full professor at the University of Tours. He's a specialist in operations research and more especially scheduling problems. And today, the tutorial will be about the meeting between operations research and databases. Vincent, the floor is yours.
Thank you very much. So, as Patrick told you, I'm a researcher in operation research, and I think that most of you don't know what it is. So I will first introduce that. And more precisely, I'm working on scheduling theory, which is a part of operations research. And the last years, I've been involved in projects with colleagues working in databases. And so what we were interested in was how we can use operations research to improve the solution of some database problems. Okay, and so that's the aim of this topic. So as you can guess quickly, I'm really a dummy in databases. So be gentle with me on that, and I'll be gentle with you on operations research. Okay, the goal is really to give you a taste of what is that field, operations research, and what you could do possibly in your researches with these tools. Okay. Also, we have to come to an agreement. This is a tutorial, so at any point of time that you have a question that I'm not clear or that you have a remark, please stop me, okay, and ask your question. So we have time to see all that, to discuss all this stuff. So what I'll do first is that I will, well, for sure, introduce operations research in a very, very general way. And then we go for a first part. There's two parts in this presentation. First part goes from 1 to 4, and I will just give you the basics of operations research, okay? The main notions, the main kind of algorithms, what we can do. There will be a lot of examples. And then in the second part, we'll switch to two applications in databases. The first one is about optimization in horizontal partitioning problems in data warehouses. And the second problem is about exploratory data analysis. Okay, just two simple problems so that you can see how these two topics can interrelate. Okay, so let's go. Before exactly defining what is operations research, just a bit of history. Operations research is a research field that dates back mainly from the beginning of the 20th century. Okay, so we can find the first works on that topic at this time, but it really grew up since the Second World War, because not only of the Royal Air Force that research on how to integrate new technologies in radars, and not only on how to position radars along the coast to detect the German activities. And so started the first optimization problems that at this time our British friends called operations research. Okay. And after the Second World War, I mean, a lot of interest has been gained in this topic, and now it's really very well studied research area. But what is operations research? So, I mean, if you ask the question to 10 of my colleagues, you'll have 10 different answers. Because the term dates back from the Second World War and from a specific application. If I have to define that, I would say that, in fact, OR deals with the development of advanced analytical methods to solve decision and optimization problems. So if you have an optimization problem, let's say, to solve, that is mathematically well-defined, then you can use the tools from OR to solve your problem. Okay, let's say it this way. And personally, I say that OR is a synonym of combinatorial optimization, discrete optimization, even continuous optimization, mathematical programming, constraint programming. So if you know any of these words, you already know a little about operations research. Okay? Just to know, is someone in the room already knew before operations research or one of these topics? Or is it totally new for you? One person, two people, 3, 4? Great, so we can stop here. We can go for a coffee break. Okay? No, I'm kidding. Continue, for sure. So the mainstream is how we can use mathematics and algorithms to build models of a problem and to build algorithms that solve the model that you have designed. So solve your problem. That's the main thing we're going to see. So a first example, I ask you to play a little, okay? So we go gently. I suppose you go for hiking, and so you have a backpack, and your backpack has a capacity of 22. So the unit doesn't matter. It could be meters squared, it could be kilos. We don't care. That's 22. Okay. And you have a set of objects here that you could put into your knapsack, but you can't put all of them. For each object, what you have is the size of the object. So this is sugar, a box of sugar, and the size is 5. So if you put this object in the knapsack, it will remain only 17. Okay? And the value here is 30, and the value corresponds somehow to the the energy that brings this meat if you eat that. So if you eat all sugar, you'll have an energy of 30 for your hand. So what you are interested in is selecting some objects to put in the knapsack so that all the objects that you put fit in the knapsack, and you maximize the quantity of energy that you have for your hand. Get the problem? Okay, so you have 10 minutes. Tell me what is the optimal solution of this problem. What is the best choice that you can do? Well, personally, I'd like to put the M&Ms in the backpack, but see, it's a good choice. Is there anything that you could already say looking at the objects without even computing the solution?
Well, the value of 30 is the highest, and the size is relatively kind of like high, but it's all right.
Yeah. So, would like to put we could think that putting the sugar is a good idea. Small size, high energetic value, that's a good deal. What else could we say?
7.
The 7? Well, sure. The bottle of water, we don't put it in the knapsack, that's sure. It takes space and brings no energy. So for hiking, no water, that's the rule. Or you put the water not in the knapsack, okay? So yeah, what we can derive is that in an optimal solution, this object will not be included for sure.
Could we not like divide value by size and then go through that? If we take the list, sort it from the highest to the lowest, yeah?
That's a good idea. That's a good idea. Keep that in mind for the second half of the first part of the presentation. That's a good idea. But if you do that, you'll have a solution. The question is it the optimal solution or not? Okay, so if you think about that, you could say, okay, so I may take the ones with the largest ratio, value divided by size. Okay, and then possibly I'll take the sugar. I may also put something like this cake, these biscuits, and then you fill the knapsack and you arrive to a solution. That would be a nice way to solve the problem. But not sure you'll get the optimal solution. That's still a pending question. We'll see later on what is the answer to this question. Okay, so in fact, the optimal solution is this one. So you put the sugar, you put what else? Packet of biscuits, I think, bananas, apricots of the biscuits, and a light salad. That's surprising, but that's the case. Possibly the salad went into the knapsack because there were no other room for better things. So okay, I have space, I put the salad, something like that. And the total size is 21, so that fits into the knapsack, and the total value is 75. So that's a very basic example, very simple to understand. And sorry for me, but no minutes in the background. That problem is a fundamental problem in the present research. It is called the 0-1 knapsack problem, okay? Or knapsack, or KP in short. So we have an input to our optimization problem. The input is the data that you are given before solving the problem. And in the input, you have a finite set U of objects. For each object, you have a weight. So the weight is what we call here the size, WG. And you have a profit, which is the value, PG, for each object. And you have a maximum capacity for the knapsack that we denote by big W. And the goal is to find a subset U prime
of objects, so such that the sum of the weights of all these objects is lower or equal to the capacity of the knapsack, and you maximize the sum of the profit of the selected objects. Okay? So do everybody understand the problem? We're okay with that?
And one object, a given object can be selected only once.
Yeah, that's it. You can duplicate M&Ms to put that in the backpack, and you can't increase the size of the backpack to put the M&Ms. Everything is fixed. You only have one object and one backpack. Okay? One copy of each object. Well, let's take another example. And this example occurs during the lockdown in 2020. So you're at home, and you have 2 bedrooms, 3 bedrooms in your big apartment or house, and 1 kitchen, 1 living room, 1 store, and 1 bathroom. And so here I denoted the bedroom 1 is by 1, bedroom 2 by 2, living room by 3, and kitchen by 4. So I only consider these rooms. And here in this matrix, you have the matrix of distances in meters, for instance. So to go from 1 to 2, so from bedroom 1 to bedroom 2, from here to here, that's 4 meters. You have to walk for 4 meters. From bedroom 1 to 3, 3 is the living room. From bedroom 1 to the living room, that's 4 meters. 4 meters, 4 meters, 4 meters. So wherever you go, that's always 4 meters. Okay. So you have a matrix of distances, you have rooms, and the question is, suppose that you live from bedroom 2, and you need to visit exactly once, each one. What is the smallest distance to? So you live from bedroom 2, and you have to visit bedroom 1, kitchen, and living room, and go back to bedroom 2. You understand the smallest tour? The sense of this is the lowest distance you have to walk to see all the rooms.
So that's 16.
Yeah, in fact, that's maybe a too easy example, okay? All distance 4, 4 rooms only. But the goal of this problem is really to say, oh, in which order do I visit the rooms so that at the end, my tour will be the smallest possible, okay? So suppose lockdown is over, and now we have to solve a bigger problem. So you have to visit cities in Spain, and you have that distance of that matrix of distances between cities. So here's a map. I don't know if you see clearly, but you have red points here corresponding to the cities that you have to visit, which are also summarized here. 1 is La Coruña, 2 is Gijón, 3 Arrow, and so on. And you have the distances here. And ask you the same question. I want to visit exactly once these cities. So what is, suppose I live from La Coruña, for instance. What is the smallest one? I don't continue until you give me the answer.
Need a computer for that.
No? For sure, you can't solve that. I mean, the previous plan was really easy because it was always 4 meters, 4 rooms, so any tool was optimal. Here, you face a real problem because you can't solve that just looking at the map. You really need a computer, and you really need a good optimization program to solve this problem. This problem is called the traveling salesman problem, or now, because of gender issues, traveling salesperson problem. But I'm sorry, I'm used for years to say traveling salesman problem, so I say traveling salesman's problem. So in this problem, you have as an input, you have a set of n cities, and for any cities I and g, you have their distance that is denoted by dig. So you know the distance in kilometers to go from I to g. Okay, that's what you are given, and your goal is to find a tour such that any city appears exactly once in this tour. At the end, you go back to the starting city, and the total tour, the length of the total tour is minimum. So just to explain the notation, ds square n s square n plus 1, well, let's say more, or here, more s ds square I s square I plus 1 means the distance between the ith city in the tour S to the I+1 city in the tour S. So if you think about ranking the cities, you say I'm a city in rank I will go to the city of rank I+1 in the solution, so you have to count these distance, and you sum all these distance, okay? And you want to minimize that. That's the same prime of a tracking salesman person that would have to compute his 2 visiting customers. That's the same. And that's the second fundamental problem with open source research. So if you know these 2 problems, that's a good start. So these 2 problems, you can roughly formulate them as either maximize an objective function or minimize an objective function. In the knapsack problem, what we wanted to do is to maximize the sum of the contributions of the items of the objects. So it was a maximization problem. While for the TSP, what we have is that we want to minimize the length of the tour. So we have there a minimization problem. And for each of these problems, we can say that the set of solutions is clearly defined. So any solution X belong to a set S of solutions. And this is the point. In operations research, we need to assume that Fx is mathematically well defined and that the set S of solutions is mathematically well defined. Okay? So when I want to explain, for instance, to my students when operations research can be used and when machine learning can be used, what I say is that, for instance, take the delivery problem at Amazon. Okay, we all know about Amazon. They have a really huge delivery problem, which is an optimization problem, and everything is well defined. You have trucks, you can't put more items in a truck that a truck can contain. Trucks must organize their tool to deliver on time. So this is well mathematically defined. So this is operations research. But on the other hand, if you consider the prime where you have a trader that is just trying to buy and sell auctions, I mean, the way the value of an auction varies cannot mathematically well define. So your prime of maximizing your income based on selling and buying auctions, this is not mathematically well defined. You can't set up equations ruling the way auctions vary. So this is more AI. You must more have to take all the data that you have from the past and try to predict the future. Okay? In OR, we really need to have everything well defined. That's the start. Okay? If you can do that, you can use everything that I'll show you after. When we have this kind of problem, we have 2 options. Either we define, we set what we call an exact or optimal algorithm, and this kind of algorithm will compute the optimal solution to your problem. So you can't do better than the output of this algorithm, this kind of algorithm. Sometimes, I would say most of the time, it's not interesting or relevant to compute the optimal solution of your problem, because you can't. I'll explain you later why. So in this case, what you do is that you design a heuristic algorithm. And the heuristic algorithm should work quite quickly. I know precisely what I mean by quickly. But you lose the guarantee that the computed solution is optimal. It's a good solution. Okay? So you have this choice. Either optimal, but you may have to pay an exponential computation time, or polynomial computation time, but you lose the optimal guarantee. Okay, this is the trade-off. These are your 2 options. When you have an optimization problem like that, also the first question you have to ask yourself is, what is the complexity of my problem? That's really the starting point. And if you have not the answer to this question, you can't go further. When you have answered this question, usually we ask ourselves this second question: what is a good model for my problem? I mean, the knapsack or the TSP, I just stated them naturally, but then I have to build a model of them, mathematical model, and I may have several options, and depending on the model that I set up, the algorithms will have different efficiencies. So the model influences the quality of the algorithms you have after that. Well, due to time, I will not have a lot of time to talk about that, but at some points in my presentation, we'll discuss a little about the influence of models in the solution process. And third point, what kind of algorithm must I set up to solve my problem? Well, we start by first notions about complexity theory. Okay? That's who knows complexity theory here. Almost the same who know about comparison switches. Good. Complexity theory, in my point of view, is something that is fundamental to any computer science research field. So if you don't know about that after that tutorial, you're fired. You channel off the job. Okay? Let's say like that. Complexity theory is a research field on its own that offers tools to qualify the complexity, the time complexity that a computer will spend to solve a problem. Okay? And somehow, when you work on complexity theory, when you work on optimization algorithms, you're trying to avoid doing HPC computing, as we have seen at the session. Okay? Because there is a strong link between solution time and complexity. And HPC can't be the solution to the complexity of your problem. And we'll go more into detail about that. So I need to define several notions before giving you the valid definitions. Well, to a problem like the knapsack, let's take the knapsack as an example. We have the notion of an instance I. An instance is the collection of data that you are given as the input of your problem. So for the knapsack, an instance is the set of objects, the weights of all the objects, the profit of all the objects, and the total capacity of the knapsack. When I give you an instance, then you are able to solve the problem. If I change the instance, you solve and you get another solution. Okay? The size of an instance is denoted by n, and that's the number of elements of the instance. So for the knapsack, that's the number of objects. That's easy to quantify. I also need to introduce the notion of magnitude n. And magnitude n of an instance is the maximum integral value that you can find in the instance. So for instance, if I think about the knapsack, if I sum up all the weights, all the profits, plus the value w, I have an upper bound of the biggest integral value that I have in my instance. Okay? So the notion of number of objects of an instance, the notion of magnitude of an instance is fundamental to try to qualify the hardness of your problem. So just keep in mind size and magnitude. Okay? And the question that we ask when we deal with complexity theory is, what is the smallest time complexity in the worst case the computer can achieve to solve, here for instance, the knapsack problem? So what is the complexity of the best algorithm that I can design, the fastest one that I can design that will compute me the optimal solution? That's the question. Okay? Is the question clear for everybody? If not, tell me. Or if you sleep, don't snore. So we have, from the literature, we have that basic classification that maybe some of you have already seen. So we are used to say that there is a big complexity class that is called NP. I won't spend time on it. And we have P that we'll talk about, and NPC here. So let's first talk about class P. In class P, you have all the optimization decision problems that can be solved optimally in polynomial time of the instance size, n. So if the knapsack is in class P, it implies that there exists, you have to find it, but there exists an optimal algorithm that works in O of n log the n, n square, n cubed, something polynomial in n. So these problems are the cool problems, okay? If your problem is in that class, you say, okay, great. And find the optimal solution in polynomial time, okay? And then you have the good problems, you have the bad problems. And These are 80% of the primes you'll be faced with. They are in NPC, so they are complete in class NP, meaning that they are all problems in class NPC are as hard as all the problems in class NP. Which means that, said in a very simple way, that all problems in class NPC cannot be solved in polynomial time of the instance size. So if your problem is in class NPC, don't look for an optimal algorithm working in n square and cube and you'll get this. It cannot exist. So in class NPC, you have problems which are really intractable for a computer. You have two subcategories in NPC. You have the really bad guys, the strong NP hard problems, and you have the moderately bad guy problem, so the problems which are weakly NP hard. So those who are weakly NPR, they can be solved in polynomial time of n and m. So these are algorithms which are also sensible to the magnitude of the largest integral in the instance. Okay? Like if you give 5 objects to the knapsack, but the value of the knapsack is 20, it will be simpler that for another instance with 5 objects, but the value of the knapsack of 1,000,000. Okay, that's what it means. These problems admit optimal algorithms which a polynomial complexity of n and m. So they are bad guys, but not that bad. For strong NP hard problems, the only hope that you can have is that your optimal algorithms will work with an exponential time complexity of n and or m. So here you have problems that require algorithms with 2 to the power of n, 3 to the power of n, 4 to the power of n, okay? So if your prime is in class NPC and is strongly NP hard, you are totally unlucky, okay? There is no way that you get the optimal solution in a reasonable amount of time. Well, maybe everything that I told you is just wrong, because all that relies on an assumption that is called P versus NP, and that's still an open assumption. So maybe some of you know the Clay Mathematics Institute. They offered $1 million for those who will answer one of the 7 open questions in mathematics. And among that 7 open question is that question: is P different from NP or P equal to NP? This is open, we don't know. So we don't know finally if P and NPC would be the name class. So that, meaning that in fact there is no hard problems. They are just dummies trying to solve hard problems. And there may be some polynomial time algorithms, but we can't find them. That's an open question. But believe me, in the OR community, no more editor of a journal want to receive papers saying, oh, I have the proof that they are different or that they are the same. They all throw to the bin that paper. No one who are fed up about trying to answer that question. Okay? Brilliant people tried and they failed. So we admit that this is different, and we always say, under the assumption that they are different, my problem is easy or my problem is hard. Okay, that's just kind of detail. But I mean, if you don't know what to do next holidays, you can try. That's 1 minute. Okay, we're talking about 1 minute. So first question, I ask you in your opinion, just your opinion, your feeling. The knapsack problem is what? In class P, weakly NP hard, strongly NP hard. Answer D, please.
Probably weakly for small instances. Find an exact solution.
Even for a strongly NP hard prime, I mean, if for any NP hard prime with the strong sense, if I give you 3 items, you are possible to enumerate everything. But enumeration also implies an exponential time complexity, so it's not always the best pick. What do you think? Do you think that the knapsack is totally easy, or not that easy, or really, really hard? You have to try. Who thinks A? It's polynomial. Who thinks B with the NP hard? Okay. Who thinks C strongly NP hard? Oh, crazy people. And D? No D. The answer is B, weekly NP hard. The combinatorics from the knapsack, just if you understood that, just comes from I have an object and I have to say, do I put it in the knapsack or not? And so the number of options, if you think about the number of options, it's 2 to the power of n. Okay? So that's exponential, but that's not n factorial. That's not n factorial. Okay? It's not polynomial, but it's not super hard. It doesn't look like super hard. So it means that the knapsack can be solved by a polynomial time algorithm, but polynomial in n and n, the magnitude of the biggest integer. In fact, this can be solved by dynamic programming. We'll see that later on. And with a time complexity, which is in O of n times w, n being the number of objects, and w the capacity of the knapsack. So you can see that if you, for 2 instances with the same number of objects, if you increase w, then the algorithm slows down. Okay, it takes more time to compute the optimal solution. And if you look at the state of the art in the OR community today, we can solve the knapsack problem with up to 100,000 items and this value of the largest integer, and this in less than an hour of CPU time. So this is a prime that can still be well solved. Yeah?
How realistic is that instance with 100,000 items?
That's a big hiking. You have a big backpack. Or very small
No, but
object.
to real problems. Is okay, you have in reality, the problems that you solve in the industry, for example,
Yeah.
are they smaller than this?
Yeah, for sure. Yeah, for sure. And I must confess that usually in real life, you don't need the knapsack naturally, but you need the knapsack as a component of a more complex problem. And so you can use these fast algorithms to solve sub-problems of your real life problem. And so 100,000 is really large. You are quite good with that. You can use this algorithm to solve your original problem.
But if you have the Amazon with a large, with a large logistics center with lots of warehouses.
Yeah, but then the knapsack, you really have to look deeply to find any of this problem. Because the Amazon Prime is so huge, so complex that possibly it's a part of it. Like if you say, I want to load trucks, I have capacity in my trucks, so what can I put in the truck? This is a kind of knapsack. It's called bin packing, but it's a kind of knapsack in this case. But it's much more complex than that. Amazon is just intractable. It's really huge. Okay, just to give you a flavor of where we can go now with a modern computer to solve this problem. We continue with the TSP. So the TSP is in class P, so polynomially solvable, weakly NP-hard, or strongly NP-hard. Please don't choose me. Not yet. Wait for that. So who thinks A, B, C? Great. For sure, when you think about the TSP, you think, my God, that's a permutation problem because I have to sequence all the cities. And the number of permutations is n factor. That's much worse than the number of options that I have with the knapsack. So possibly it's harder. And you're right, that's really a hard problem. So you can't solve that. So you can't solve in an optimal way. So get the optimal solution. You can't do that in a polynomial time of n and m. You have to pay for exponentiality. And what we know is that the best known algorithm works in 2 to the power of n. And even to reach 2 to the power of n, we spend several days just to understand how it works the algorithm. Okay. And we are able to solve some instances, not all, but some instances with almost 86,000 cities in size, and not all. I mean, that's very tough to solve. And in 286 days of computation. So you feel the difference between weakly NP-hard and a strongly NP-hard. That's not the same difficulty. Yeah?
So I assume that this is without additional real constraints that from city A to B you can travel not faster than there is no highway. So it's assume that every row is the same.
Yeah.
It's the same.
Yeah.
Right.
Yeah, and no additional constraints. Very simple version of the problem. If you add constraints, that's even harder. In practice, you just can solve on the average instances with just 100 series in size. So you really get stuck by combinatorics. So some golden rules. If your prime is shown to be in class P, then you're lucky, and you really have to find what is the optimal algorithm that works in polynomial time of n. You really have to find that, and that's the only option that you have. If your prime, that's it. If your prime is in class NPC, don't search for a polynomial time exact algorithm. You want optimality, you have to accept that the best you'll be able to do is to design an exponential time algorithm. Either pseudo-polynomial like the knapsack, or fully exponential like for the CSP. That will be the price to pay. So the nature of your prime influences the kind of algorithm that you have to design and what you have to look for. In operation research, we have a toolbox of methods that we can use to solve problems. So exact algorithms for NP-hard problems, so branching algorithm, mathematical programming, dynamic programming, and so on, or heuristic algorithms, so these algorithms that loses the property of computing an optimal solution, but then they work in polynomial time. You may already have heard of some of these words. That's cool. What we'll see is mathematical programming, dynamic programming, constructive algorithms, and neighborhood-based algorithms, some of them, then just to illustrate the purpose. And that's it. I'm trying not to keep time for the second part. So exact methods, mathematical programming is a very useful tool to derive solution algorithms. That's the basic thing that you have to do when you're faced with an optimization problem. And that when you want to compute the optimal solution for NP-hard problem. Okay, I don't talk about solving exactly polynomial type problems, because these are very particular. The way you derive an exact algorithm is very particular in this case. So I focus on hard problems. You can build an IP, mathematical program, and then give it to a well-known black box solver like Cplex from IBM, Gurubi, Express. Well, you have many of them. Cplex and Gurubi are mostly certainly the most efficient ones. So first, what we have to do is to build a model of our problem. We first start with the knapsack. When you have to design a program, the first thing that you have to do is to say, okay, what is my combinatorics? And I need to define a variable that will enable to model this combinatorics. So for the knapsack, naturally you say, oh, the combinatorics come from the fact of saying, I have an object, I put it in the knapsack, or I don't put it in the knapsack. So I define binary variables that says that xg will be equal to 1 if item g, or object g, is selected, and 0 otherwise. So I define n binary variables, and I ask to the solver to instantiate these variables, to give me the optimal values of these variables. And for that, I will say, okay, dear solver, maximize the sum of the profit of the selected objects. Pg is the data, it's part of my instance. Xg is my variable. And then, what you'll have to answer is this constraint. The object that you'll put to 1 here, the sum of the Wg must be lower or equal to the capacity of the knapsack. And I say to the solver, all the variables Cg belong to the set 0. They are good. Okay, dear solver, no, solve the problem. And the solver will solve the problem and give you the optimal solution. So that's pretty cool first when you have a problem to solve. And this IP, this integral program, is almost as efficient as the best exact algorithm that we talked about, which is based on dynamic programming. So this is really easy to solve. Now, if we apply that to the TSP, we could also do an IP formulation for the IP of the TSP. That's a bit more tricky. What comes the complexity of the TSP? Where it comes from sequencing. Okay, so I have a permutation problem. Okay, so possibly what I can do is introduce binary variables xij, which are equal to 1 if cti is visited right before ctg. Okay, so if x34 is equal to 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 Okay? And so my IP is the following one. I want to minimize the total distance of my tour. And I say that each city has at least a predecessor, and each city has exactly one predecessor, and each city has at least one successor in the tour, as it is a tour. The successor of the last one is the first one. So, okay, I have another IP formulation here that I can give to my solver. If I think about it, I could also do it in a different way. I could also say, okay, I still introduce n-square binary variables, but then I have xik, and xik would be equal to 1 if city I is visited in position k in the permutation, so in the list. So if x34 is equal to 1, it means that the fourth visited city is city 3. That's another way to model the problem. If I model it this way, whoa, that's quite heavy. That's the IP. I don't know for you, but I prefer the previous one to this one. More constraints. You have kind of big N constraints, I would call them in OR. That's nasty for a solver. If you give that to the solver will do bad. Don't solve that. Okay. I can solve that for 5 cities and then I stop to this. That's why I told you before. The choice of the model really influences the way you can solve the problem. Okay. Dynamic programming, and maybe go a bit quick on that. We'll keep time for the second part. Can be useful. It's very different from mathematical programming. NP is really easy, really. And now solvers really work quite well. So first thing, go for an IP, try to build an IP, ask yourself the question about what generates the combinator rigs, what are the variables holding that, and then you derive the constraints. That's the way to do it. But you could do also dynamic programming. It's based on the decomposition principle from Bellman. That's a republication of his book because Bellman's principle is 1962, I think. We can illustrate that easily on the TSP, okay? So I'll denote by opt of LC prime, it will be a recursive function. And it will be the optimal solution value when I consider only a set of cities C prime that has to be visited after city L. And for sure, a city appears exactly 1 in the solution. So I illustrate that with this little figure. So when I have opt of L C prime, I am in this situation. I've already built part of the tour, starting from city 1, and I am now at city L. That's why I have L here. And the cities that remain to visit, for instance, is 3, 4, 5, 2, 13, 10. That's C prime. They have to go after this tour. So what I say is that opt of L C prime is the minimum value, the minimum tour, about when I put one of the city after L. So I try for all the cities in C prime, and I say that's the minimum of opt. I visit G after L. G is removed from the remaining cities, and I add to this length the distance for going from L to G. Okay? Just get the raw file, it's enough. And you iterate like that. That's a recursive function. And to solve the TSP, you just have to compute that, which implies computation of all the other intermediate values of opt. And if you solve that, then the time complexity is equal to the number of states. That's 2 to the power of n. That's a simple version to get to do. So if you have an example, to sketch an example here with 3 cities, we first start from city 1 and we say, okay, I want to compute opt of 1, and it remains 2, 3 to visit. So I say, oh, that's the minimum of 2 options. First option is that I visit city 2 after 1, and the second option is that I visit city 3 after city 1. If I visit city 2, then I have to compute opt 2, 3, and I add the distance between 1 and 2. And if I visit 3 after 1, I have to compute opt 3, 2, and I add the distance d1, 3. Okay? Then I have to compute opt 2, 3. And you obtain that. That's the distance of 7. Believe me. Opt 3, 2, I apply the same principle, every distance of 6. So now I go backward and I say, oh, now I'm able to compute opt of 1, 2, 3. That's the minimum between 7 plus D12. D12 is 4, 7 plus 4. And the minimum with opt 3, 2. Opt 3, 2 is 6. 6 plus D13. D13 is 5 plus 5. So here, that's a particular case, okay? Here, any tour 1, 2, 3 or 1, 3, 2 has the same distance. Okay, yeah?
This matrix is always like two-dimensional, yeah?
Yeah.
Always.
Yeah. Well, there are a lot of variants on the TSP, so I'm saying that, but maybe there's a variant I don't know, which is different. Okay, on the knapsack, you could do the same, getting this recursive function, and so you can easily program that, implement that, and then you solve the problem. And this works in NW time. This is the very famous DP algorithm from Kissinger. That is the state of the art in the domain for this problem. And there are a lot of other algorithms. I have no time to dig into these, so stop there for exact algorithms, and we'll switch to heuristic methods. That's in fact all you need to know. The first one that we'll see are the simplest one. They are called greedy heuristics. So now we're talking about algorithms that will work in polynomial time of n, the number of items of my instance, but we have no guarantee that the solution that will be computed is optimal. Okay? We hope for a good solution. That's it. And greedy algorithms, they iteratively build a solution based on the priority rule. So if we take the KP, and I go back to what you said initially, what I could be interested in is in computing the ratio PG divided by WG. PG is the profit. So an object with a high profit looks very interesting. And those with the small weights, they also look very interesting because I can put them in the backpack for cheap. So those having a high ratio, PG divided by WG, they really look like interesting objects to be put in. So this could be a priority rule. We could say, okay, I have this ratio that seems really nice to me, and I just order my items by decreasing value of the ratio, and I take the items one by one in this order until I fill the knapsack. And if I do that on my example, what I do is that I put 1, 2, 3, 1, 2, 3, because I have a weight of 3, and I can't put anything else. My capacity is only 6 in this example. So I start with 1, 2, 3, and the total profit is 9. Okay. Is someone thinking that this algorithm would be optimal in the room? Do you think it's an exact and optimal algorithm? Tell me the truth. What is in your mind?
You may have to reshuffle some stuff at the end when you have gap between your optimal capacity and like last few items.
I think that all of you slept during the previous part. This problem has been shown to be Euclidean pure. So it can't exist at polynomial time exactly. And this algorithm works in polynomial time. That's n again. That's a sorting. So this algorithm can't be optimal. This algorithm can't guarantee that any time you call him, it will compute the optimal solution. That can't happen. So what we know is that 9 is a lower bound on the optimal solution. Maybe there is a solution that is better than 9. This we'll see later. And in greedy algorithms, they are very simple. You just have to define your priority and build a solution guided following that priority. And you can also have dynamic priorities, so that each time you select something, each time you take a decision, you recompute your priorities and you update them, and you continue solving that. They are very, very simple algorithms. Okay. They have they are very basic, so that's kind of a drawback, and they can easily be improved by more elaborated algorithms. Okay, but that's the first type of heuristic you should think about. But the main advantage is that they scale up to very, very large instances because usually they work in n log n time or n squared. So they can handle instances with a huge value of n. And that's cool, man. They are really convenient for very, very big problems. Well, what we have also are local search heuristics. This is another kind of heuristic that you can try to design. They work in a different way. They start with an initial solution and they try to improve that solution. So typically, you could think about designing a greedy heuristic to get an initial solution, and that solution, you give it to a local search heuristic that will improve the solution. That's very classic, very common. How work local search? I'm sorry if you don't see clearly in the picture, but suppose that this is the solution space. You have the initial solution that is given to the local search that is called S0. And then after some iterations, you are at another point. So let's say iteration T, I'm at point ST. In local search heuristics, we need to have the notion of neighborhood to be defined. So the neighborhood of solution ST is this gray circle. And you at iteration T, you look in this neighborhood to an improving solution, ST plus 1, for instance, here, and you iterate. So you kind of have a walk in the solution space. Let's illustrate all these notions from the previous example. So I can take as an initial solution S0, 1, 2, 3, total profit 9. And suppose my neighborhood operator, so I need an operator that defines the notion of neighborhood. And here I'll take the swap operator. What is the swap operator? The swap operator takes an item in the backpack, takes an item outside the backpack, and just try to swap them to build another solution. So the neighborhood of 1, 2, 3, when I use swap, is all the swap that you can build from S0. That's that. Okay? So what you have to do is to find in this neighborhood a solution that improves 1, 2, 3. And that is feasible with respect to the capacity constraint for sure. So the best solution is 1 to 4. And 1 to 4 has a total profit of 30. Just swap 3 and 4. So the notion of neighborhood depends on the operator you choose. I mean, depending on your prime, you have many possibilities. And that's also part of your job when you solve your prime to decide which operator is the most effective for the problem. But that's the main one. And if you iterate this process, you stop at S1 because in the neighborhood of S1 there is no improving solution. So it was a really small example. Of course, searches, they are more time consuming than greedy heuristics, for sure, because you have this notion of neighborhood explorations, and these explorations may take real sometimes, depending on the operators that you have for the problem. But they are quite common to use. They scale up also to large, not very large, but large size instances, and they are quite effective. In fact, the combo greedy and local search heuristics is the perfect heuristic that you should start with for the problem. Okay, you have a lot of heuristics in the literature. We have no time to go and present all of them. The tip of the day is, in fact, when you design a heuristic, I think that even in the OR community, a lot of people are just forgetting that when you design a heuristic, you have to take account of the size of the instances that you want to solve in practice. I mean, if I have an instance that is just made up of, in my real prime, I don't know, 10 items, and n equal 10, and you match heuristics, genetic algorithms, any kind of algorithm works, even the slowest ones. But if I have, for instance, a prime accumulating database with hundreds of millions of items, I mean, you can forget about that, you can forget about that, forget about everything. And the only heuristic that you may be able to use are greedy heuristics, because they will be the only one that scale up to your prime. So the size of the instances that you have to deal with is very important in the choice of the heuristic you will use. Okay. Now we go for the first application case. So I enter a domain where I'm less confident. Okay, that's database. So if I say wrong things, if I use the wrong word, please say nothing. You say okay, that's okay. Okay, and I continue gently. I just hope that you'll be able to understand what we did, and so we use that later on in your own projects. So the first problem is the horizontal partitioning in data warehouses. This follows a work from Nigel Benatrech and Pascal Richard, mainly who are colleagues, and we also worked a long time ago with them on this problem. So we elaborate on this work. So we have a simple data warehouse defined by a star relational schema. So we have the fact table and we have dimension tables here. And we are given a set Q of selection queries QG that are frequently run on this data warehouse, okay? And the goal is, the question that we have been asked by our colleagues is, well, how can we partition the tables so that the processing of any query in Q is as fast as possible? How can we do that? That was the question that we have been asked. Well, so first question, what is the complexity of this problem? Oh, strongly NP hard. So, okay, that sounds good. So we do with that. So no way for polynomial time algorithms, no way for pseudo-polynomial time exact algorithms. So either we solve it to optimality and we'll pay for full exponentiality, so we'll have something that runs in 2 to the power of n, 3 to the power of n, something like that, or we go for heuristic algorithms, the optimality problem. So we just give a little of notations before explaining what we did on that, what could be done. So for each query QG, we have a set of ng of predicates I that are defined like that. So predicate GIK is defined by an attribute AIK of the dimension table K, an operator theta equal lower and so on, and a value V of the domain of AGK. Okay. We also are given a way WG or query QG, which reflect its frequency. So queries that comes really often, then they have a really high weight. And we also have a bound W on the number of partitions that we want to generate from the table. This is an accessory data, but it was also given to us. Okay? Don't create more than big W partitions. So what we do is consider direct partitioning of the fact table and see how we can build a mathematical programming formulation of them. This is what we mainly did. So what we did first before building the mathematical program is that we analyzed all the predicates of the queries to build all the possible of what we call elementary partitions. I'll explain that. So for a given attribute AK, we define QK, the set of all predicates PGIGK for any query, so such that the attribute K is involved in the predicate. So you look at all the predicates and you say, oh, here you have A1 that appears, A1 that appears, A1 that appears. And we put that in Q1. That for the second attribute, and so on and so forth. And we partition the domain AK in disjunctive subdomains according to QK. So we create NK subdomains that are distinct from each other. We partition all the possible values of all attributes depending on the predicates. And at the end, we create that number of values, the products of all the NK elementary partitions by partitioning products of the subdomains. I just give an example. I mean, for me, it's nightmare to do that. So consider we have these three queries, okay? Select blah blah from where, and we look at all the predicates here. Age lower 25, town equal to tour, name not equal to Pablo, and age greater than 12, town not equal to Paris, and price lower to 100. So for each attribute we have, so for the first attribute, which is age, we have Q1, age strictly lower than 25, this is what we have here, and we also have age greater to 12. Town, we have equal to tour, not equal to Paris, that's what appears here. For the name, we have different from Pablo, and for the price, we have strictly lower than 100. Okay, this is what we have from all the queries. Then what we do is that we partition the domains. So the subdomains of A1 are age between 0 and 12, 12 and 25, and 25 equal plus infinity. This is partitioned according to that. We do the same for the town, the same for the name, and the same for the price. And so here, what we have, is that we have 3 subdomains for attribute 1, 3 subdomains for attribute 2, 2 subdomains for 3, and 2 subdomains for 4, meaning that we'll have 36 elementary partitions. 3 times 3 times 2 times 2. We'll have all the possible combinations. So that's all the elementary ways to partition the tables. I will not do that, there are too many partitions. But that's the starting point, okay? And next, what we say is that for each query Q, for instance, Q1, we say, okay, Q1 requires reading elementary partition, F1E, F2E, F3. So we can attach to any query all the elementary partitions that will have to be read. And from that, we build level 1. So our key variables are the following one. We have binary variables ULG, which is equal to 1 if the F elementary partition is part of the G partition I will create. So the FG are the partitions I will create. I know the FLE, which is the input of my model. I built that initially. I give that to the model, and I ask the model to create the FG. And I said, this ULG is equal to 1 if in the G partition I put the elementary partition FL. Okay? And 0 over this. And also have VGR equal 1 if the G partition I create has to be read when I read query QR. So this is derived from that for sure, but this is also a data that I need, a variable, sorry. And what I want to do is to minimize the cost of processing my set of queries. So I want to minimize the sum of all queries of the weight of the query times the size of the partitions that I will have to read to answer queries. Okay? So this depends here. This depends on the way I will have gathered the elementary partitions. That's the optimization plan. I decide how I group the elementary partitions. Oh, this is the IP that we had in the end. But it's not nice to look at, okay? Don't worry, I'll not ask you to understand everything, just to show you that it's, oh, there are mathematics, right? Yeah, don't worry. And this model has a prime, it's not a prime, but that the number of binary variables depend on that product. So on the number of elementary partitions. And if you followed what I told you before, just before, the number of elementary partition is a Cartesian product of numbers. So it grows very, very quickly. So the number of variables of this model can really blow up very quickly. That's the drawback. And what I did just when I prepared this presentation is that I implemented this model and I ran it one of the latest version of Cplex on my computer and said, okay, let's see which kind of instance I can solve with that. So I did something that is very common in our community, but that you may not like, but I don't care. Is that we randomly generated data warehouses. Okay, I don't explain the protocol, but I randomly generated data warehouses saying, okay, it could be like that, trying to capture all the possibilities. Okay, it's not the way you do, that's the way we do. In ISP, I do as I want. Okay, so I started with 2-dimension tables. Each table is randomly assigned between 2 and 4 attributes from 5 to 20 queries. So these are very, 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 very small problems, very, very small data warehouses. I don't care about the number of rows in the tables, just the size and the shape of the data warehouse matters. Okay, and for each number of queries, we randomly generated 30 instances. And I impose a CPU time limit of half an hour to the solver. And this is what I had. So that's the solution time of my solver, number of queries. And you can see that's the average CPU time, maximum CPU time, and minimum CPU time over the 30 instances here with 5 quick queries. On the average, it required 269 seconds to solve the problem. And here I have the number of elementary partitions and it was quite limited. And in fact, I had some problems just to build instances that were solvable by the IP, because if I play a little with the number of attributes, number of predicates, then this totally explodes, blow up. I mean, the model can't even be solved by the solver. It's too big. So what you can derive from that is that, okay, this is cool to have a MIP, mathematical program, but here can't solve real life problem. It's just for fun. The advantage of this IP is that it is independent from the number of rows in the tables, and that's pretty cool, because in the data warehouse you have a lot of rows in your tables. So don't use that in real life applications. That was the conclusion of what we did. So we can think about improving that. How could we improve this model? It works well, not super well, but what could we do? Limit the number of elementary partitions to create. Yeah, that's a good idea. If we limit the number of elementary partitions, we decrease the size of the IP formulation, and so we increase the chance that the solver is able to solve the model. So we could say, oh, if you look at that, oh, look at the name Pablo. We would just want to ask for in the queries that the name is not Pablo. So could we eliminate all the elementary partitions in which we have Pablo? Because we're not interested in having Pablo. We don't want to have Pablo. That's a terrible idea. If you do that, you discount some rows that may appear that may be part of others, the two other queries. So you can't do that. Oh, okay, bad idea. What can I do? Well, if I think about, for instance, the first weight, if the first weight, so the query one, the weight of query one, is really high, like superior to the number of, to the size of the fact table, then what you can derive, what you can prove, is that in an optimal solution, all the elementary partitions related to Q1 will be gathered in the same table, and you only put that in the same table, because then you'll only read the necessary rows, and so you'll minimize the objective function. So this is correct. You can do that. You can, under certain conditions, you can eliminate some elementary partitions. So it opens the door to maybe think differently to the problem and try to find mathematical conditions to reduce the number of elementary partitions. Well, we can build an IP based on all the paradigm, but it's not a good idea. That's very terrible. I mean, if you put into the game the number of rows, like what I just sketched here, that's a bad idea, because the number of variables will be so huge that you can't do anything. I think that the best idea is still to limit the combinatorics by dealing with the elementary partitions and try to limit that. For the IP, I'm scared that it's the only option that you have. So maybe the best thing is to just go for heuristic algorithms and try to design a heuristic algorithm to solve your problem. You will not have the best partitioning, but maybe you'll have a good one. So what you can know also is that this prime has some similarities with the knapsack problem, because you have to select objects to put in a partition or not. And there's a notion of number of limited partitions. So somehow we could also explore the fact that we know well how to solve the knapsack problem. I mean, if you're interested, you can work on that. We didn't do anything this way. Second problem is the exploratory data analysis. And so this is based on a work that we have in common with Nicolas Labroche and Patrick Marcel. Alexandre Chanson is a PhD student that we supervise, that is about finishing his thesis next December. So we are in this plan, we are given a database and a set queue of all comparison queries. So when I prepared the slide, Patrick told me you should introduce more comparison queries. Oh, okay. So comparison queries apparently are very popular, and they lead to this kind of tables in the end where you can compare numbers. You can compare numbers for different columns and different rows, and you have nice properties on them. So we only consider the case of this comparison query. Okay, but you know all the possible comparison queries for your database. You have a database, you have all these comparison queries, and we start from here. And then EDA consists in finding a sequence of queries that you can run to maximize the interest of the provided insights at the end of the processing of all the queries. To each query QG, you associate the processing time, so the time that you need to run the query, and you associate also an interestingness score, VG, that is the interest of running the query G. And to each couple QG, QK, you have a distance DGK. The distance, you can see it in a way like that's the difficulty for a user to understand why you run query K after query G. So for some queries, it's easy to understand that, okay, I do K after G, that's sent. Sometimes it can be a bit tricky. So what we want to do is to say, somehow we want to minimize the difficulty of understanding this chain of queries. So we want to minimize the sum of all the distances of the query, not to do something stupid when we compute this series of queries. And so our problem is just to find a permutation P of n prime queries. So n prime being smaller than n is the number of all the queries that we are given, such that among this permutation, we have maximized the total interest of these queries. We have minimized the total processing time of the queries that we have selected. And we minimize also the difficulty to understand P prime, so the sum of the distance of all the between the selected queries. Okay, that's the plan that we have. And this problem is a multi-objective one because we have 3 objective functions. And it has been shown to be strongly NP-hard. So again, we're unlucky. By the way, I mean, if at the moment you don't know what is the complexity of your prime, just put a coin on the fact that it is strongly NP-hard, and 90% of the time it will be hard. Okay, most of the primes are strongly NP-hard. So what we do, what we've done is that we set up an epsilon constraint approach to compute the Pareto optimum for these 3 criteria. I go fast on that. That's not the point of the presentation, but what it is that we maximize the total interestingness subject to the constraint that the total processing time is upper bounded by a constant that I call epsilon t, that is given by the decision maker. Like the decision maker says, well, I don't want to spend more than 10 minutes to run all the queries. Okay, so what can I do with that time? That's the epsilon t. And I also have an upper bound on the total distance. Okay, and what I know from multi-objective optimization theory is that an optimal solution to this problem is a Pareto optimum for my 3 projects. So it's an interesting solution. So what we can do for this problem, again, we can sketch up a mathematical program, an MIP. So here, I don't know if you saw that, but this problem is a kind of a mix between a knapsack and a TSP. Because on one hand, we have to select queries. And on the other hand, for the selected queries, we have to order them to minimize the total distance. So that's a kind of a mix between the knapsack and the hybridization of the knapsack and the TSP problem. That's cool. So we need variables, y. 2 equal to 1 if query I is selected, and 0 otherwise. So these are the variables from the knapsack. And what we have done also is that we have introduced a binary variable xij equal to 1 if query I precedes query G, and 0 otherwise. And these are the variables that will enable to solve the TSP part of the problem. Okay? And here it is, this is your problem. This is the problem of the EDA problem. Want to maximize the total interestingness, have my constraint stating that the total items must not exceed the bound on the computational time. That's the constraint bounding the total distance. And these constraints are just to define that you can select only once an item, when you have to sequence the selected items, and that's all. Okay. Number of binary variables, that cardinal of q squared plus cardinal of q. So you can think that it's pretty cool model. But it depends on the number of queries. And if you think about that on the database, the number of queries can be quite huge. So again, this model looks simple, but as the number of variables depends on the number of queries, that's not sure that you can use that model to solve your real-life problem for a given database. But if you do computational experiments with this model, you can see that it's limited to a few hundreds of queries. So if for your problem you have thousands of queries, well, this model will not apply. Okay. Okay, that doesn't work for a real-life problem, but what we can do is to look more closely at the mean, and as I said, the red part is the knapsack. That's the knapsack problem. And in blue, that's the decision version of the TSP. And this, we can exploit that to build heuristics. What we will do is that we'll take heuristics for these two problems and we'll combine them to solve our problem. First heuristic is called HKS, and it's inspired by the KP, like knapsack. What do we do? Suppose that you have 5 queries, and this bounds on time and distance. I'll do like the heuristic the greedy heuristic that we've seen before. I will just compute the ratio. So that's not PI, that's VG divided by TG. It's wrong here. I compute the ratio VG divided by TG, and I take the one with the largest ratio, and I select the corresponding query. I take the second highest ratio, so Q2, and I say I will process it. So you see what I do. I sort my queries by decreasing value of the ratio, and I start. So I have here my distances for the TSP problem, and I said, okay, I select the first query, Q1, great. Next, and that's the first step, so I have nothing more to do. I just go to the second step. Second step, I say now I select Q2. Okay, so if I select Q2, I have to check. Sum of processing time is equal to 2. That's lower than 6. My bound here, so I can select Q2. Okay, I select Q2. Then I have two options. Either I put Q2 after Q1, or I put Q2 before Q1. I'll test that. Possible insertions of Q2. And I choose the best one. Well, in this case, they are the same total distance, so I randomly choose the first permutation, Q1. Then I iterate. I select the third query, Q3. Sum of processing time is 3, lower than 6, it's still feasible. I have 3 possible insertions. I can put Q3 first position, Q3 second position, Q3 last position. If I put in the first position, total distance is 7, that's feasible, right? If I put in second position, total distance is 11, Q2 is not feasible. I will not consider this possibility. And if I put Q3 in the last position, total distance is 10. That's higher than 8, so I can't consider Q3. So what I do is that I have no choice. I can only keep P1. And I iterate like that. And in fact, the heuristic will stop with this solution. That's a mix of the knapsack and the TSP. That's the way we did that. Possibly you can find another way. Possibly better than that. That's cool. Do it. Maybe for you a new paper in the conference. What is the efficiency of this heuristic? What we've done is we have generated random data, and on the average, that's the deviation, the average deviation of the heuristic to the optimal solution. So here, for 300 queries, we are at 0.07% of the optimal solution with this heuristic. And it works in 0.017. So that's a really fast heuristic that is really close to the optimal solution. In practice, this heuristic is really good. So I'm not sure you'll do a paper on that. Right. And scales up very well to large set of queries. So we can solve about 1.5 million of queries in a few seconds. So it becomes interesting. So you could think about other greedy heuristic algorithms. You could think about local search. Which kind of neighborhood operator could we use? Well, you could think this way and try to do something different. We've done a lot more than that for sure. We've done also a match heuristic based on the IP. We get even better results than the greedy heuristic. We saved the world and everything's fine. Okay, but you can do a lot with that. The primary idea is that the generation of queries is really time consuming, meaning that before being able to run the heuristic, before being able even to build the IP, you need to have the set of all queries and generate all the comparison queries. If you look at the CPU time, it was like 99% of the CPU time and 1% of the CPU time just solving the problem. So we said, oh, that's pretty unfair because we just spent our time generating the queries. So what we have also investigated is a way to avoid building the set of all queries. We start with randomly generated queries among the set of all possible queries, and we have a special procedure that says, oh, the next query you have to generate to improve the solution is this one. You generate the queries, you generate another query. So you generate only queries that improve your current solution. And at the end, you build up this procedure when you have all the queries. You have something even better, and you avoid generating all the queries. If you want to know more, that's the PhD of Alexandre. So you can ask. Okay. And to conclude, so database theory is full of optimization problems. I think that you know already. So I think there's a huge room for collaboration with people working on operation research and people working on database. Because the question is, how can I solve my optimization problem? And you may not have all the elements to answer efficiently this question. But all the people have. They know nothing about database theory, but they know how to solve optimization problems. Now you can't say that you don't know about OR, okay? So you can say, now I still continue working on my optimization problems with the things that I know for years, and I don't change. No, you have to change. Right? I hope I gave you the appetite for going further with OR, either by yourself or by working with colleagues who know about OR, for sure. A little feedback, and I stop with that, is that when we started to work on this problem, I came with my habits. Like, okay, we run genetically random data to test the heuristics, and we have behavior on the average of our algorithms. And finally, it appears that this doesn't work with your problems because your problems are very particular. You say, oh, I take one database and I solve my problem on this database. But your database may have very particularities like equal values, a lot of equal values, or a lot of zeros. And these particularities make really different the way to solve the problem. I mean, if I want to solve a problem, whatever are the value of the data, I'll do as I do in operation research. If I want to solve your problem, I have to take account the particularities of your databases. And this at the beginning, I didn't have that in mind. This has to be kept. And also, it's very challenging because you don't deal with instances with 10, 100, or 1,000 objects. Your instances have millions of objects, millions of queries, millions of rows. And this changes really the way what we can do with the tools that we have. So that's very, very challenging. Thank you for your attention.
Thank you very much, Vincent, for this very didactic and insightful tutorial. I hope we have a couple of minutes for some questions from the audience.
Thanks for the very, very nice tutorial.
Thank you.
And just one question, because I understand that all you explained was about the integral programming.
Yeah.
That's my understanding.
But I spoke a lot about that.
Yeah. But you mentioned also linear programming and quadratic programming.
Yeah.
I don't know if you could explain more or less the difference.
Yeah.
And exactly, my question was about the quadratic programming. I may be wrong, okay, but that's this is what I wanted to know. My understanding that quadratic programming or linear programming is related to the cost function, to goal, let's say, but not to the constraint.
Depends.
Is it, or so what has to be quadratic or can be quadratic or
Okay, I've been pretty fast on that, so that's normal. Mathematical programming is a general word to say programming. Okay, so in that you have linear programming, and in linear programming we assume that all the variables take real values. Okay, and the constraints and the objective function are linear. That's linear programming. In the integral programming models that we have seen, all the constraints and the objective function are linear, but some variables can be integer or real, and that changes everything. Linear programs can be solved in polynomial time by itself. Integral programming or mixed integral programs, they can't be solved in polynomial time. Okay, and they both are linear. Quadratic programming is different because you may have either the objective function or constraints or both, which are non-linear. As much as you can, stick to linear models, because there is a galaxy of difference in efficiency of solvers. If you have a quadratic model, then solvers are just shit. As long as you stay in the linear world, it works well. So if you can avoid to model your program in a quadratic way.
For a question?
Thank you very much for your very nice presentation. So one question is about your experiences in application of operations research in pre-optimization problems, in cost-based optimization algorithms. Do you have any experiences about heuristic algorithms that are applied in that area to find an optimized execution path of your query? And
What you mean by cost optimization based?
Yeah. In cost optimization problems, you need to consult also some statistics about attributes and their distributional values in the domain.
So I'm not sure if you fully understand the question, so I give you an answer, you tell me if this is the right answer, okay?
Maybe, okay,
But-
discuss. But typically, cost optimization algorithms use some heuristics for calculating the execution value and to find the best one according to the value.
So I think. So this is maybe what we call stochastic programming.
Yeah.
In stochastic programming, for instance, you assume that you just know like laws about values of some execution time, interestingness, and things like that. And so you may have to think in terms of probabilities. So you have to for instance, to maximize the expected value of the total cost, or minimize the expected value of the total cost. That's an option. You also can find works where you have what we call robust programming. Robust programming, you say that an item takes value in a given set, but you don't know exactly what will be the real value. And so when you optimize, in this case, you optimize to minimize the worst case scenario. And you say, okay, I compute your solution, and I guarantee you that whatever is the final scenario for the values, you'll be at the most at 10% of the optimal solution for this scenario with this solution. So this kind of thing also is done. That's next level with comparison to that, but there are works, yeah.
Thank you. Another one also about some criteria that include mandatory items. For example, sometimes you have mandatory items and optional items.
Yeah.
So some of them must be inside, and somehow it reduces the problem. But if you know by your domain knowledge, you can declare some criteria as mandatory and some others as optional.
Yeah.
Do you consider that?
No, that's easy. That sounds easy to integrate.
Yeah. Sometimes it greatly reduces the problem.
Yeah, for sure. If you know that you have to select some items for any reason, then you say, if the knap's like, okay, I take the M&Ms, I don't care. I want just to have the M&Ms, so I select them. Then you compute the best option, the best solution with this constraint. This can be done easily.
I have been told that we have to shut down the session and go to the lunch. If you have any further question, I think Vincent, you will shut down as well. So
I'm here.
Thank you so very much, and thank you again.
Thank you.